Well, hello. Welcome to another little video segment. This one is going to show an actual good application of Gauss's law, and that is to derive electric field expressions for, in this case, charged up spheres. And there'll be other videos that you can use to see how it's done for charged wires or very long lines of charge, cylinders, things like that. And then another one for a very large sheet of charge, or maybe parallel plate capacitors. The process is very important. It's not about the equation that you end up getting. It's not a formula in any way. It's very much a process. And you'll see questions written that way. It'll say something like, show how to use Gauss's law, rather than, something simple like just to derive. So I do want to emphasize that. And here's the first situation that I've laid out for you. Imagine we have a ball of charge, solid metal ball of charge, positive 4 Qs, and then surrounding it is a hollow shell of charge, also made of metal, some kind of conductor, that we have charged up to a negative 6 Q charge. So opposite charges on the different parts. And when we draw these shells and spheres, it's very difficult with 2 dimensions to make it look right. So they'll look a lot like circles, but make sure you read the context of the problem. And if you, as you're drawing it, want to add a little 3-dimension effect, if you can do that, that's great. The high-priced graphic artists that do the textbooks are able to do that as well, but there's no expectation that you can do much beyond what you see here on the screen. So if it's not drawn for you, make sure you draw it. And then let me show you the kinds of questions that you would be asked about this. Imagine you have this little dot. We're just going to move it around for the sake of the conversation. Somebody might say, use Gauss's law to figure out how strong the electric field is at that dot if we put the dot somewhere inside the solid metal ball in the middle, what they call region A in this situation. Or a different question is, what if we put it in the cavity between the 2 hunks of metal, cavity they call region B? How strong would the field be there? And similarly, region C inside the actual metal of the shell, or somewhere out here outside the entire arrangement, what they call region D. I'm going to do region D, but the process I'm going to show you could work for any of those 4 regions. So the process starts, once you've got a diagram, by imagining what we call a Gaussian surface, and it has to match the symmetry of your charge situation. So since we have spheres of charge, we will draw a Gaussian sphere. Now I've actually got one drawn here digitally, but you could do the same thing just by hand. Make it very light, because this is not a real piece of metal. This is not a real anything. It's more like just a mental construct that we use to help us do a Gauss's law problem. And what's important is that the Gaussian sphere be centered on the actual metal spheres and also go right through wherever the dot happens to be. So if your dot is way here in region A, you would draw a tiny little Gaussian sphere. But we've got a dot way out here outside the whole arrangement, and so I'm going to expand this a little bit bigger and make sure that I can make it coincide with that dot. So I'm going to have to go a little bit bigger. This is a lot easier if you're just drawing it yourself, because you can make sure it goes there. And I'm also going to cheat here by just moving the dot a little bit inward. So there is my Gaussian sphere surrounding my metal. Then the process goes like this. Now, here's what we write when we do a Gauss's law problem. You start with a statement of Gauss's law, and the most formal one looks like this. Now, it looks very calculus-like, but it really is not supposed to be. There's no calculus that you actually end up doing here. What it says on the left side is the entire electric flux through some closed surface. That's what that means. Electric flux through a closed surface. Our surface is this imaginary Gaussian sphere. And the flux, we've talked about that. That's just the product of the field times the entire area through which that field is piercing times the cosine of the angle that each field line makes with an area vector. So we'll deal with that in a second. And then on the other side, we have the charge inside. Now that's what this in means, and it's very important. You look at all the charge that is enclosed within your imaginary Gaussian sphere, and that's what goes into the numerator there, and then our familiar epsilon sub naught permittivity constant underneath. So why do we not use calculus here? Well, we have carefully made the situation so that we don't have to. We have spherical symmetry, which means we would expect the electric field to be the same at that dot as it is if we put the dot anywhere else on that sphere. I mean, why would we expect to have an electric field different if I put the dot here versus moving the dot over here or over here? That means I don't have a bunch of different electric field values there. I just have one number, whatever it is, and that's actually what I'm looking for. The other thing is, the electric field vector should point radially along a line from the center, which is exactly the same direction that the area vector would point, radially outward or inward. In this case, the area vector has to point radially outward by the convention that all area vectors point out from a closed surface. So that means we don't have to worry about the directionality piece. And then when we get rid of those, what we end up with, and this is not really necessary to write, but I'll write it just to be explicit, means we can take the e outside of the integral because it's just some constant, whatever it is. We can ignore the dot product in the vector notation, and so we just end up getting the sum of all the little areas. And again, those areas mean the areas that we add up around the entire Gaussian sphere. Well, what is the area of a sphere? It's 4 pi r squared. So r is some distance. I'm going to use small r here. Well, no, I think I'll use capital R because they use small r's to denote the sizes of the spheres in the problem itself. Okay? And I'm going to label this distance there as my big R. So that's the area of your Gaussian sphere. And then over here, here's a very important step. What is the entire amount of charge enclosed within that Gaussian sphere? Well, it's everything that we saw here, the positive 4 and the negative 6 together, which is a negative 2q in total. And then we put that over the epsilon sub naught. And then if we do a little algebration, solving for e, we get 1 over 4 pi epsilon sub naught, 2q with a negative sign, put the negative out here, over r squared. Now I've put the symbols in little different places, but I did that on purpose so that you could see, we recognize that as the symbol for k that we use, the electrostatic constant. 2q is the total enclosed charge, the magnitude of that anyway. The negative here tells you which way the electric field vector will point. Negative means towards, radially towards the center of our circular region. And then r squared means it's inversely proportional to how far our dot is from the center of that. So when all is said and done, you should recognize here, this is just the same thing as the electric field of a point charge, as though all of the charge that we have were concentrated in one small spot at the center of that circle, a total of negative 2 q's there. And that's the beauty of Gauss's law. It shows us or demonstrates why that simplification works. So every spherical problem you do is the same. The only difference is, where do we put that dot? Which means how big you make your Gaussian sphere, which also determines how much charge you actually enclose within that sphere. Now there's other situations we can do, but I think I'm going to leave it here because I've shown you the nuts and bolts. Your textbook will have an example of what happens if you're inside a non-conducting surface, but I don't think I'm going to include that here, just get a little too lengthy. So hopefully you can replicate that process when the time comes. If you have any questions, of course, you know where to come and find me.